Dear students, okay, welcome to the Edu Saradhi. So I'm Vijay as a physics faculty. I'm here. Okay, so today we are going to discuss electricity from 10th class CBSE concept. Okay, so we'll start electricity. Okay, okay. So just we'll go to the small motivation. So nothing in life is to be feared. It's only to be understood. Now is the time to understood more so that we may fear less. Okay. So this is a great quote given by the Mary Curie. Okay. So as we know, she got the first woman, she got the Nobel Prize from physics and chemistry also. So what she's saying, so if you do understand any concept which is difficult, okay, so we can able to overcome all the difficulties. Okay, so that's what we are going to start this chapter. Okay, now, so our main contents, now we are going to discuss in this chapter: introduction, electric charge and electric current, electric potential and potential difference, and Ohm's law, resistance, okay, combination of resistors which is in series and parallel. So and final topic is heating effect of electric current and find electric power. Okay, directly we'll go to the our concept. Okay, so as you know, so when we talk about the electricity, first we have to start with the charges. That is a electric charge. So what does it mean? Okay, it is a fundamental property of a body which experiences a force or other. Okay, so what is this one? See, any body, suppose any kind of the body, like we are talking about the mass of is a property of the body. So like so here, so it's a charge is a fundamental property of a body which experience force of attraction. Okay, so here repulsion is there, it's a attraction too. Okay, and so SI unit of electric charge is coulomb, so that is represented by the C. And majority, so as we seen, okay, charges are classified into two types. One is a positive, another one is a negative. Okay, and so actually when we talk about the charge, so we have to think what kind of charge, I mean what is the cause of the charge. So if you take about the charge, we think, so charge, it's a due to the proton or deficiency of proton. It's not about proton, it's about the charge is due to the excess of electrons and deficiency of, okay, electrons. Okay, so that is called, that is the body which occurs its charge. See, they have charge of one electron. Charge of one electron is a minus 1.6 into 10 to the power of minus 19 coulomb. Okay, and 1 coulomb of charge, suppose if we take the 1 coulomb of charge, then how many number of so electrons will be present, that is 6.242 into 10 to the power of 18 electrons will be there, okay, in 1 coulomb of charge. Okay, so let's see, so when we talk about this one, okay, so we'll see. Okay, suppose we'll see one example. Suppose an object has gained 5 into 10 to the power of 18 electrons. The total charge on the body will be. So actually how to find the charge of the body? As we know, okay, it's a charge is nothing but it's a fundamental property of the body. This is because of due to the, okay, deficiency and excess of electrons on the body. So now we'll see that how to find this charge. Actually they given, okay, how many electrons will be there. So electrons are, okay, so electrons are 5 into 10 to the power of 18 electrons will be there, and the total charge on the body. So suppose if you take this is the body, so you can take the charge on the body is present. How many number of electrons will be there? This much is there. Now what is the charge of the body? So how to find the charge of the body? So as we know, there is a simple formula, that is a total charge is equal to, so number of electrons into its charge. Okay, number of electrons into its charge. So as they given, now how many number of electrons they given? 5 into 10 to the power of 18 electrons will be there. Then what is the charge of each electron? See, what is the charge of each electron? That is the charge of the electron is negative. That is the reason minus 1.6 into 10 to the power of minus 19. So they can, now we can see directly. So what is the total charge here? Then we can see this is the 0.8 coulomb. So this is the charge of body. When you are getting these values, so you have to calculate the what is the total charge on the body. Now we'll go to the next very important concept, that is the electric current. So when we talk about the electric current, so what does this mean? See, that means that there is a flow of charges from particular cross section of area of a conductor in unit time. That is a electric current. So that means that if we take, okay, so if we take, this is a any conductor, okay, any conductor. So as we know, the cross section of the body, that is, this is a cross section of the body. So this small portion, or so this is a cross section of the body. Then, so suppose if the charge is moving, so it's flowing from this end to, that's A to B. See, so number of charges flowing, so per unit time in given cross section, that is called electric current. Okay, so it is a, so given the definition also, I mean mathematical formula also they given. So what is this? If the net charge, see already we have calculated what's the net charge. Charge is nothing but that is a Q, okay, is equal to n number of particles, which is what are the fundamental particles like electron or proton. So into, okay, its charge, okay. So SI unit of electric current, that's ampere. Whenever you are I mean writing that unit, first you have to write with the small letters its name, okay, and you have to indicate with the capital letter its unit, okay. So basic question actually in the board point of view, okay, every time they will ask this kind of question like what, define the 1 ampere of current. So what is the 1 ampere of current, how to define? So this is the, you have to define, so flow of 1 coulomb of charge per 1 second, per second, that is called 1 ampere of current, okay. So and so there is a, how to measure this kind of electric current. So there is a separate device is there, that is a ammeter. Ammeter is that helps to measure the electric current in a circuit, okay. Then so which position we have to connect? See, it should be connected always in series, okay. So we'll discuss the what is the reason for connecting in series, okay. So next, so direction of electric current. See, as we know, direction of electric current in the ancient times, okay, what they consider, so they consider that conventional electric current. First they stated that, okay, so actually the positive protons are traveling, okay, based on that direction, proton they consider as electric current. Actually there is a no proton is moving, so there is a due to the electron flow the current is racing. So in ancient time, that is a, okay, in 18th century, that time itself they consider that is a charges is flowing from positive to negative, that is a, based on that direction they consider that, that is a conventional current, electric current, that is taken from positive charge, okay, direction of the positive charge, okay. And electronic current, okay, electronic current, this is the actually, so what is the direction of electrons, which direction the electrons is moving? That means okay, electrons will travel from, so negative terminal to in a battery, so positive terminal. So that is what direction of the electric current. And we'll see on small numerical question here. So here an electric bulb draws a current of 0.2 amperes when the voltage is 220, I mean 220 volts they given. Then calculate the amount of electric charge flowing through it, okay. So they given in 1 hour. See, so the basic formula we know, that is the, so that's I is equal to Q by, okay, this is the formula. So they given, just the given, so voltage, okay, but we don't require that any work in this given question, okay. They're asking that amount of charge, then the charge Q is equal to I into T. See, so now Q, so I is how much they given 0.2 and time, so time is how much they given, 1 hour. So 1 hour, so we have to convert into the seconds, because SI unit of coulomb, that is, okay, I mean SI unit of charge, that is a coulomb, That coulomb is comes like ampere into seconds. Okay, we have to take time is also in seconds. That is the reason. So we are taking 0.2 into so 60 and 60. So how much you will get here? So here you will get a 720 coulomb charge. So how much charge, total charge that's flowing through it, okay, in 1 hour, that's 720 coulomb. So as we know, in 1 coulomb, that's a 6.25 into 10 to the power of 18 electrons will be there. Okay, so this is what the small question based on the formula. Next, so very important concept, that is the electric potential and potential difference. Okay, so I will give some analogy to understand what is this concept of electric potential and electric potential. Okay, a potential difference. See, as we know, if suppose a horizontal pipe you keep, okay, you send the water through it, then what happens? Actually, in horizontal pipe, the water, if it is a, there is no any difference in the height, then what happens? There is no flow of water through any pipe. Same like that. So same when there is a same potential, see both the ends is that same potential will be there. So in the wire, so if you take this wire, okay, if the both ends the potential will be same, then there is no, okay, flow of any charge, like same thing like so here electric pressure we call it as electric pressure is creating the potential difference across the two ends of conductor. Okay, so why it's important? Okay, because if the charges need to move in a given conductor, so from one end to another end, so then external energy we have to give to the body to move from one end to another. So that is a potential difference. Like we are keeping the water, I mean water tank at the top of the building. So and we are taking the water from the ground level. So because of we are making the difference in the potential energies. That is the reason, because of that difference, it's travel, the water travels from high potential to low potential. Like same here also, the electrons whenever we are taking the, in the battery, so battery we are considering the positive terminal as a high potential, okay, and so negative terminal as a low potential, then always the charges starts moving from high potential to low potential. So that's what same phenomena here also it appears. So that is the definition of this one. Okay, so here, so actually that is the electric potential difference, so between the 2 points in electric circuit is a work done, so to move a unit charge from one point to another point. So suppose if you take this A and B 2 points, okay, then how much the work needed? So how much work needed? So how much work needed to travel unit charge from one place to another place? That is called electric potential difference. Okay, so electric potential difference. So that is a mathematical formula. So that is a, so V is work done by unit charge. So work done by charge, that is equal to so potential difference. So what is the work done? So work done is equal to so potential difference into it charge. Okay, SI unit of potential difference, that's a volt. So volt it's a named by, so this I mean, so Alessandro and Volt from Italy. So he discovered this, I mean, concept of potential difference. So that's the reason they given the name. Okay. Next, our important concept, one more in the entire in electricity, that's Ohm's law. So based on the Ohm's law, we have seen the n number of numericals and n number of application from the Ohm's law. So as Ohm's law is discovered by the scientist name called Simon Ohm. Okay, he's from Germany. So he discovered the relation between the how current and potential difference across a conductor. So here we can clearly we can see, first we will go to the graph what is giving. Okay, so suppose if you take, see what happens at the 0 point here. Okay, so when the current is 0 and potential difference also 0. Okay, so and when the current is increasing our potential is increasing, suppose if you take then automatically so the graph is also, okay, it is, okay, increasing. So from this relation, actually this law is based on experimental, okay, experimental based law, this is proved experimental only. Okay, then so what is this? The potential difference occurring inside the metallic wire in an electric circuit is directly proportional to the current flowing through it. Okay, that's the condition the given. So you have to understand that is a constant temperature. A constant temperature only. So the potential difference across the two ends of any conductor. Okay, then the that is directly proportional to the how much current is flowing through it. Okay, then so this is the V is directly proportional to I. Then so if we given one more relation, see, so Vi. So if you take out this one, then V is equal to that's somewhat K constant I. Then K is equal to that's a V by I. So and he given the name of this constant also. That constant name is called R. So that is R is nothing but this is a resistance. Okay, this is the resistance. Okay, so what does this mean? Okay, resistance which oppose the okay which oppose the flow of charges. Okay, it oppose the flow of charges in a given conductor. So that is called resistance. Okay, so always you have to keep in your mind whenever vi you draw a vi graph. Okay, that's potential difference versus I current I, then always it should be constant. Then the line should has to travel through okay origin. Then it should be past the origin, because when there is no potential difference the current is also zero. So then it is only, so the special case is only at constant temperature. If the temperature is not constant, then the graph will be not same. Okay, so now next so we'll see about the so resistance, the new concept. I mean, just now we discussed about the resistance that opposes the flow of electric charges. So same thing, how the electric, I mean resistance will depends on the okay factors. What are the factors? It will depend. Okay, so the resistance of the conductor is depends on okay, it depends on okay its length of the wire. Suppose if it's a wire length, suppose this is a wire length, that's the L if you take. Okay, so that means that the resistance of the wire is directly proportional to its okay, so it directly proportional to the length of the wire. And how it depends on the area of cross section. Okay, so it depends on the area of cross section, how R is inversely proportional to the A. So R is inversely proportional to the A. Then what is this A actually? So there will be some, I mean, small confusion students here. So what is this area of cross section means? So here the cross section area. So this is, if you take, this is the cross section area, this area, not complete area of a wire. Okay, it's just a face. Okay, if you take the one face, that is the area of that particular cross section. So always the wire will be in circle in shape. Okay, that means the area of cross section is circle, but its shape is cylindrical in shape. Okay, so next, and it depends on the nature of the material. See which material we are using. See, so suppose if you are using the copper, if you are using the aluminum, if you are using the silver material, so based on the property, that resistance will vary. Suppose if you take the insulators, so insulator the resistance is almost very high, so it will not allow the flow of charges through it. So when you take the conductors like silver, I mean copper, so they are very, I mean good conductors, they will easily travel the, I mean any charges through it. Okay, so that's what. And okay, and it depends on the temperature too. Okay, so you can write here, it depends on okay temperature also, temperature, because temperature varies. Okay, it is also depends on the temperature. And so here we can write so R is directly proportional to, so L, directly we can write the formula R is directly proportional to the L, then R is inversely proportional to okay 1 by A. So and directly we can write R is directly proportional to L by A. If you remove this proportionality symbol, then we'll get rho. So that is the rho. So rho is nothing but here. So this is a rho. Okay, so this is a rho. This is called another new constant. This is called okay electrical resistivity. Okay, electrical resistivity. So that is called rho. So this is the property of any material. So based on any property, if you want to take up any property of the any insulators or metals and semiconductors or alloys, okay, all these quantities based on based on the electrical resistivity only, we can say what kind of the property it is. See, and SI unit of resistivity, so that is electrical resistivity, that is a ohm, okay, meter. So ohm meter, how will define this is, see, you can take the rho is equal to, so you can take this from this relation, okay, from this relation rho is equal to, so R into A, okay, R into A by L. So what is the, okay, units of resistance, that is a ohm, and this is a meter square, and okay, that is a ohm meter. So this is a, okay, so factors it, so what are the factors, it depends, okay, resistivity only depends on the nature of the material and temperature of your body, okay, it only depends two factors. But electrical resistance, that depends on the, so length and cross sectional area, nature of the material and temperature. But here resistivity only depends on, okay, so it depends on nature of the material and temperature of a, that temperature at given temperature. So now we'll see that one small problem, okay, so this is also very important problem, okay. Now we'll see the what is this given formula, okay. In the following figure, three cylindrical conductors A and B and C. See, this one A, this one is B, this one is a C. If these three are conductors made up of same material, so what you have to understand from here, so that means that, so same type of material, that means that resistivity is same, the resistivity is same. And so Ra, Rb and Rc, their respective resistances, then find out the given ratio. First we have to find Ra by Rb, so this one we have to find it, okay. Now we'll see what is this Ra. First we'll find out the what is the Ra. So Ra, it's a, just you have to find, so given length of the, I mean material, that is a L, then rho, that's L, and this area of cross section A. Then what about this B, Rb? So Rb, so that is a, see, rho, rho, same rho, so resistivity same, rho into L by 2 and 2A. Then Rb is equal to, okay, rho L by 4A. Then RC, then RC is how much they given, so they given, so rho L by 2 and area is A by 2. Then this is equal to, okay, rho L by A, okay, because 2 to get cancelled, because it comes up, then 2 will be down, then it will get cancelled. Now we have to find, so first thing is we have to find RA by RB. So what is RA by RB? So RA is how much? Rho L by A. So RB is how much? So RB is rho. So that is a L. Take the same L. Okay, L by 4A. Then rho L get cancelled. A get cancelled. Then what will get here? Then you will get 4. The ratio RA by RB, that ratio is 4. Then second one, what they given? So second, so this is what they given, RA by RC. So what RA? So RA is how much? Rho L by A. So RC is how much? So this is RC, that's rho L by A. Then this everything get cancelled. This is the one. So the ratio RA by RC is equal to 1. So this one. Then if you have any doubts, you can message in the comment box. Okay, so one more question we'll see. Okay, so if a wire of length is L and area of cross section A was drawn into the wire of double of its length by melting. So the given, so it drawn double of its length by melting. Then if it's a original resistivity and resistance were okay, so original, this is a rho actually. So take this rho. So rho and R respectively. What will be the new resistivity and resistance? See, so now we'll see this question. Okay. So now as we know, so resistivity, okay, resistivity. So resistivity depends, so depends only on okay nature, okay, nature of material and temperature. So that means that here, okay, resistivity, it does not depends on the dimensions. That is the reason the resistivity will be, so initial how much it is there now, so final also same. Okay, final also same. That is the first one we got it. So same resistivity, that is a rho. Okay, so next okay, resistance. As you know, resistance, it depends on the dimensions. Then R initially, R is equal to rho L by A. Okay, rho L by A. Now it's a very important to understand this kind of problem. So here, so its length is changed. Suppose this is a wire. Okay, this is a wire. So length of the wire is L. Now, okay, its area of cross section, that is a if you take it. Okay, now it's by melting the length is doubled. So that means that, so its length is doubled. Then what happens? So the wire, okay, the area also will changes. But what is constant here? That's a volume. Okay, volume is constant. So volume is constant. So volume is constant. We have to write the relation based on the volume. So as we know, R is equal to rho into L. So now area, its length. See, this is the length, and this cross section area will give the value. I'm multiplying both the side L. Then this is a rho L square by V. Okay, then V is a constant, then we can write directly, and rho is also constant, then we can write R is directly proportional to the L square. Okay, then we can write so R1 R2, that is a L1 square L2 square. Now we need to find, so R2. So R2 is how much? So that is a R1 into L2 square, then L1 square. Then so R1 is nothing but it's R, you can take directly. Then L2 is how much? Its length is okay. So its length is doubled. That means that okay, that's 2L square, then L square. Then this is the 4 times of initial. So if the length is doubled, then what happens? Its resistance is 4 times of its original resistance. This is R2. Okay, based on this one, you have to find this. Okay, next, okay, one more question we'll see. Okay, this is also very standard question, so very important. You can take very important question. Okay, and when the potential difference of a 2 volt is applied across the ends of a okay wire of 5 meters okay length, a current of 1 ampere flows through it. Okay, suppose now we'll see. Okay, suppose this is a wire. So this is a wire, this is a A, and this is a B. Okay, then so this length is also given, this length is given, L is equal to 5 meters. Okay, then so this is connected to battery 2. Okay, this is connected to battery, that is how much? 2 volts is connected. Then so current is 1 ampere they given, so 1 ampere, that's a 1 ampere flowing through it. Okay, so next, now we have to find the how much the resistance of a wire. So we'll see first option. So first subdivision. So the resistance per unit length of a wire. They're asking. So what is the R by length? So how much resistance per unit length they're asking. Okay, now we'll see this one. First thing is we need to find what is the resistance of wire AB. So resistance of wire AB, that is equal to, okay, so as we studied, that is Ohm's law. Okay, so V, okay, by I. Then what is the V? V is equal to, so 2 volts, then I is equal to 1. That means that, so resistance 2 ohms. Okay, the resistance is 2 ohms. Now we need to find first subdivision. That means that resistance per unit length. Then how much resistance we got? 2. How much length is that? 5. Then, so 2 by 5, so that is a ohm meter. Okay, ohm per meter. Then this is also we can write 0. Okay, 4 ohm per meter. This is the first division. Okay, we got 0.4 ohm. Okay, because this is second division. Okay, 5 4 is 20. So like, so next second subdivision. Okay, that is the resistance of 2 meter length of the wire. So how much? See, as we know, we got this entire wire. So this is 5 meter. Then if you, I mean, make into 1 2 3 4 5 5 subdivisions, that is you can divide into 1 meter. So 1 meter, so 1 meter, 1 meter, and 1 meter. So, and you, how much you will get? So 1 meter, how much resistance we got? 0.4. Yes or no? This is 0.4 ohms per meter. Then they're asking how much? 2 meters. Then resistance, you have to find per unit how much? 0.4 ohm meter. Then how much they're asking? 2 meters. So they're asking 2 meters. Then meter get cancelled. Then 2 fours are 8, 0.8 ohms. So this is the second subdivision. So and so this is the one. So third one, so we'll see. So third one, okay, the resistance across the ends of the wire, if it is doubled to itself. Okay, so here there is no changing. Okay, it's length. They're not saying about anything about the length. They're saying it's double by itself. So how it is possible? So how it is possible? Huh? So if you take this is a conductor. Okay, so this conductor is A, then cross section is, I mean, length is L and cross section is A. Okay, then if you double, I mean, wire, then double, now how will you do double? Okay, you can't stretch, because they're not saying by stretching, they're not saying by melting, or it's not saying something else. It's saying about doubled by its own. Means that here it is like how it is possible. There is only one possibility that we can do by folding. Okay, we can do by folding. So by folding, how much you can get? See, so this A and this A. So by folding, it's doubled by folding. Then length will decreases by L by 2. This is L by, I mean, if it's a double na, so its length is, I mean, reduced by L by 2, because we cannot reduce its length. Okay, it's doubled by its own. We have only one option. We can have to fold. So next, so you have to find out how much resistance. So as we know, R is how much we got. So we got R is equal to, so RAB, that is equal to 2 ohm. Okay. So now we can find out this one, same thing, that is R is equal to R dash. Now new resistance. So this how much cross section area? See, now this entire one is cross section area A plus A. So that's a 2A. Then if you're changing its length, okay, so by its own there is no change in its resistivity. That means that it's a rho. Okay, so length is how much it's decrease L by 2. Then area is how much it's increase, that's 2A. Then R dash is equal to, so that is a, so rho L by 4A. Then this is equal to rho L by A, because as we know, R is equal to rho L. So if you take this L and this one take, if you take this cross section area of wire, so this one is a cross section area of wire, this L. Okay, we take any cross section here. So now we can take this one is a, okay, so rho L by A, that is directly we can write 2 by 4. That means that 2 it's a 0.5 ohms. So this is 0.5. So you can write down, doing pause here, you can write down this one. Next, so we'll go to the another important concept, that is the resistance of a system of resistors. Okay, so first we'll think about, see, we have that how many, so usually these are resistance, this are resistance R. Okay, then this R1 if you take, now you have one more resistors. Okay, so resistor, one more resistor you have, it's R2. So this resistance is R2. Now you want to combine this one, you have to combine both. Then how it's possible? So one is it is possible, okay, by connecting alternatively, then one into another end. So one end, see, this is A and this is B. So and one more possibility will be there, that is so one is connected like this, if you take this R1, and one more is connected same from this point only we can connect, one more is. So how many possibilities will be there? We can connect the resistance, okay, resistors, okay, of having some resistance R1 and R2, that can we can connect only two possibilities ways. One is okay, whether it is series, and we can connect in the parallel. So these are two cases we can able to see. Okay, then okay, usually the circuit you can see this is I mean you can connect n number of circuits also. Okay, like you can dash dash dash. Okay, here, so it's a series means alternative, one after one. Okay, one end of the resistor is connected to another end it's continuously it will flow like this. Okay, then here, okay, it's a parallel resistor, okay, connected in parallel. That means that you can connect one end to many. Okay, infinity you can connect, how much is required, infinity you can connect. Okay, now we'll derive the formula for these two cases. Okay, so very easy. Now you can see as experimentally the proved, so in a series, okay, in series, okay, so this is proved by experimentally in series, the current I is same. So I is same. So that is the reason, okay, that is the reason, okay, we are connecting that ammeter in series. Okay, everywhere it's connected in series. Okay, current will be everywhere in same. So we need final, okay, current, how much this, I mean current passing through a given circuit. So for that reason we need to measure the current. So that is the reason ammeter is connected in series. Okay, now we'll see here based on in this diagram. Okay, now here what happens now? Okay, now is R1, R2, R3. So now here you can see, okay, current everywhere it will be same. So here same, I here also same, and here also same. Okay, now here, so what is the difference? Okay, here potential difference will be, I mean potential difference across the each resistor will be different based on the that is the reason V1, so V2, this is V3. Okay, then combination I will write here, we can write it as this V is equal to V1 plus V2, so V3, that's a VR equivalent, final one. So as we know according to Ohm's law, that is a V1 is equal to I R1, because I is a constant everywhere. Then V2 is equal to I is equal to, then V3 is equal to I into R3. So and V R equivalent also I into R equivalent. So based on this relation, we can find out the, see, R equivalent, that is V R equivalent is equal to, directly we can write I into R equivalent. This I1 R1 plus I2 R2, then I3 R3. Okay, this I will be everywhere same, right? So I will be same everywhere. So we can take this one is I is everywhere same, then I only we can write. Then I get cancel everywhere. So you can take the common I, you can get cancelled. This R equivalent is equal to R1 plus R2 R3. This one. Okay, and in parallel, okay, it comes to the in parallel. Okay, so that is if you take the any resistance. Okay, so this is the one. Actually in parallel, so in parallel the potential everywhere will be same. So this one V2, if you take V3, so in parallel what happens now, the potential everywhere same. This V1, V2, V3 and V4. So that is the reason. So what is a measure, that is what potential difference is measured, is voltmeter. Voltmeter is connected always, it's in, okay, parallel. Now you can calculate here V1. So here the current will be, if you take this series, that's current I, here also current I. Okay, that means that current here, this I1, this I2, this I3. Okay, then so all currents will be, then I is equal to I1, I2 plus I3. Then so based on the, according to Ohm's law, that's a V1 is equal to, okay, I1 R1. There's, we know V1, V2, V3 all are equal to V. Then we can write this one is a I1 is equal to, so V by R1. Then I2 is equal to V by R2. Then I3 is equal to V by R3. Then you can write this one. So R equivalent also V by R equivalent. This is the, so V by R1 plus V by R2. This is a V by R3. Then V get cancelled. 1 by R equivalent. This is equal to 1 by R1, 1 by R2, 1 by R3. So this is the, okay, so equivalent resistance in given circuit. Now we'll see one problem. So we'll see one problem. So here the question, so what they're asking, the given circuit. Now we need to calculate what is the current I. So we need to calculate what is the current I. Okay, so now we'll calculate the current I, and we have to so for calculating I, we need to find out the R equivalent. So what is the R equivalent? Okay, here you can see, okay, so there are R1, R2, R3. Three are connected in series. But R4, so if you take this a point A, so if you take this a point B, okay, see, so from point A, how many is directly connected? See, one is connected this way, and one more is connected like this. And this is the end is connected to this one. That means that from A, 10, 10, 10, R1, R2, R3, all are connected. So these three are connected each other by series, but this R1 is connected to, so parallel to R4. Here also R3. So that means that how you calculate this one, R equivalent also we need to calculate. So first thing is we need to calculate for series one. Okay, so we need to draw the first simple circuit. See, this is a circuit we have to take. So this is a circuit we have to take. This is a R equivalent. This is a V. Now we have to find the I. So I is equal to, so how much you can take? So V is equal to IR. So IR na, this is V by R equivalent. So based on this one we have to calculate. So this is the final our formula. So we have to make this circuit into a simple circuit. First thing is, so these three are in series. Then R series, that is equal to R1 plus R2, R3. So R1 is how much? This is 10, 10, 10. So 10, 10, 10. This is equal to 30. So this is a R series. Okay, so this is R series. Now we can do it. Okay, we got 30. So this is a R dash series. Okay, first this is only for, okay, so only series only we got. Now this all things again will draw some simple circuit. Okay, here one more, and this is a one more. This point we can take. Okay, or else you can take, okay, right, you can take this one only. Okay, now here I current is flowing, so this is a R, yes, then this one is how much? R4. So R4 is how much? 10. Okay, this is a 10 ohms. Okay, now you can calculate this one is a, so how much is given? 3 also is given. Now these both are connected in, okay, these both are connected in not parallel because this is a point, so this is a B point, so both are connected from same point, so both are in parallel. It's R equivalent is equal to 1 by 10, 1 by 30. Do the LCM. So this is 3, 3. Then what will get R equivalent is equal to this 4 by 30. So this is a 4 by 30. Then R equivalent is equal to 30 by 4. Then this is 15 by 2. That's 15 by 2. This is 7.5 also we can write. So this is R equivalent is equal to, we got 7.5. 7.5 we got. Now we need to find out the what is the I. Then what is I? I is equal to V by R equivalent. V is how much we got? Okay, they given 3 volt. So that means that this 3 volt by R equivalent is how much we got? Okay, 15 by 2. Directly we can write here, we can get cancel here. Okay, this is ohm. So 3 5 is 15. Then we can take I is equal to, so 2 by 5 ohms. Okay, 2 by 5 ohms. Okay, then what will the final answer? This is 0.4 ohms. Okay, so this is the current is passing through it. Okay, next. Okay, now one more circuit is given here. Okay, so this is also important. Okay, the problem. Okay, this is important problem, that's here. Now we'll see. So given following electrical circuit is given diagram, 9 identical resistors, they given identical resistor, all are 3 ohms and each are connected in given figure. So they given, so this is a I1 they given, A1 is given, so how much they given? 1 ampere. So 1 ampere. Then so here A1 and A3, so both are connected in series. As you know, so if it is both are connected in series, that means directly without knowing anything, A1 is equal to A3 we can write. So now we'll see what is the questions. The given subdivision. So what is the relation between the reading of A1 and A3? See, okay. So A1 and A3. So A1 and A3 both are in connected series. That is A1 is equal to A3. So as we know, the current in series is same. Okay, that is the reason A1 is equal to A3. That means that this is a 1 ampere. Okay, next, so B. So what is the relationship between the reading of A2? Okay, A2 and A3. So here they are asking A2 and A3. So here you can see here very clearly we can see, if you take in this one is a current. Okay, if you take this current, okay, 1. So here what happens if you take this I2, this I3. So for example, okay, for example only I am taking I1, I2, I3. So here at this point, from this point, if you take this A point, from this point the current is dividing. That means that, okay, from this point the current is dividing, and again from this point all currents are combining. So that is the reason damn sure here we can get A3 is greater than A2. A3 is greater than A2. So this relation is enough. Okay, next the third subdivision. Okay, third subdivision, determine the reading of voltmeter. So what is the, so voltmeter V1? They're asking that voltmeter V1. So as we know, A, okay, so A3, A1, so A3 and A1 they given 1 ampere, that is in series. Okay, now we can take this entire one R equivalent, we find the what is R equivalent here. Then what is the R equivalent, that is in both are in parallel, that is R equivalent, that is equal to, so that is a see. So as we know this one we have to find. Then what R parallel, that is equal to 1 by 3 plus 1 by 3. Then what will get here? So both are same. Then RP is equal to, that's 3 by 2 ohm. Okay, 3 by 2 ohm. Then so what is the V1? Directly we can write, so V1, so okay, so V1 is equal to, so we know the current, so as we know this is the current I into, okay, so what is the resistance across here? Okay, so then we can directly write I, so I is how much? So 1, so 1 into R parallel, so that is R parallel is how much? That is a 3 by 2. Then 3 by 2, volt. This is the okay. So voltage, I mean, in across V1, okay, in this section. Okay, now, okay, so now very important, this is I mean, usually here you will feel somewhat difficult, but this is a very easy concept one if you understand. Okay, so here, so heating effect of electric current. So as we studied, I mean, as we know, so there are many effects of electric current. One is a chemical effect, one is a heating effect, and one more is a so magnetic effect. So this is majorly we can classify, but here we can see only heating effect. So what does this mean? Actually, when any circuit, I mean any closed circuit, when the current is passing through, or you can take the fan, okay, some current is passing through the fan, then what happens? After some time, it will work, and it will release some amount of heat. So that heat, I mean electrical energy, is converting into the their okay heat energy. That is called okay heating effect of electric current. Okay, suppose, so we'll see some formulas. Okay, this is also called, we can say this joule heating. So now if we take any conductor, suppose if we take any conductor, okay, so if we take any conductor, this is a length L. Okay, if we take any conductor length L, then so current is flowing through it, that is I. If we take, okay, current flowing through I, you can take, then okay, its resistance is R. Okay, its resistance is R. Now the potential difference across between these two, okay, so if you take this potential difference across between these two, that is a V. If you take, okay, then how much work is needed to move the charge? See, as we know, work, that is equal to, work is equal to V into Q. So potential difference across the conductor and its charge. See, that is a work done. So this is a work done is needed, how much needed for charges to move. Okay, then this much of work we need to do charges. So that is okay, this much of work done, that's here we need to supply this much of energy to move a charge. So that is electrical energy we have to do. So this is electrical, okay, so energy we have to do. Okay, now from this one, okay, so if you take a, suppose if you take that is a input power, I mean if you take the power input given, so that is the energy. So power, you know, that is input power, that is the energy by time. So energy by time, that is a power input, that's a VQ by T. So that is a VQ, okay, by T, that is a power. Then so then amount of heat is how much it's liberated. Directly we can say that is a okay, so heat, that is heat energy, that is equal to power into T. So power into T, so how much power is given? So that is a VQ, okay, by okay, so T into okay T. Then VQ, directly we can take VQ, that is V into Q by T, that is equal to I. Okay, V into I into T, that is heat energy is equal to VIT. So that is a heat energy is V by T. And here, okay, and here you can see here, okay, Joule's law. Okay, so Joule's law of heating. So Joule's law of heating, that is a, so how much heat energy so is liberated, dissipated in a given, okay, any conductor. That is a, as we already saw, this is a I VIT. This I mean heat energy we got. Now we can take this one. Okay, so V, according to Ohm's law, that we can write I into R. Now substitute this one, I into R into I into T. Then we can write this I square by R. So this is called Joule's law of, okay, Joule's law of heating. Okay, Joule's law of heating. So that is Joule's law of heating, that is heat liberated or dissipated, that is directly proportional to I square, that is directly proportional to R, that is directly proportional to so time taken. So charges to move across the conductor. So this is the heat produced here. Okay, and already next. Okay, so next we'll go to the electric power. Okay, so electric power, just now we already discussed, that is a amount of the rate of doing work. Okay, so the rate of doing work, so is, okay, it's called electric power. Or else we can write a rate of consumption of energy, so that is also electric power. So usually, so this is a P is equal to V into I. So that is a potential difference across any conductor, and it's a, I mean, current passing through a conductor. So if you do multiplication, you will get how much power is given. So, and we can write this also. Okay. So as we know, this is a basic formula. So this is the basic formula. That's P is equal to VI. So P is equal to VI. Then here we can write, this is the equation based on Ohm's law. This is a V into R. So based on Ohm's law, we can write this is a IR into I. This is I square R. Then one more relation we can write, this I is equal to V by R. This we can write it as also. So in place of I V square by R. Also we can write. So this is about the, okay, this is about the electric power. See, usually they will ask, that is a very usually many times this question asked. So SI unit, okay, SI already we studied in mechanics. Okay, so about the power, so power is nothing but rate of doing work. There we studied, that is a, okay, so SI unit there, watt. Here also same watt. What is the SI unit of electric power? So now 1 watt, if they ask it 1 watt of electric power, so define 1 watt of electric power. If they ask, you just write, so when it is anything, so when power consumed by the device that carries 1 ampere of current when operated, okay, potential difference 1 volt. So you can take this 1 watt, 1 volt into 1 ampere. Actually this is a very smallest unit. Okay, usually if you take this 1 V and 1 ampere, this is a very small unit. That is the reason we'll avoid using the this unit. So whenever we are taking the, so in general practical case, okay, so in the practical case will not use this will use in, okay, so kilowatt. Okay, so in practical case, most of the cases we are I mean seeing that our homes, okay, electrical energy usually we call it as 1 unit, 2 units, 3 units. Okay, that means that is a electrical energy. Okay, how much we are using the electrical energy, that is electrical energy is a power, product of power into time. So usually electrical energy is a, so watt hour. So usually electrical energy watt hour, that is a electrical energy. This is a power into time. So this is a, okay, power watt. Okay, and time, that is a H. Okay, power, I mean power into time, that's a watt hour. That is the electrical energy. SI, I mean it's not SI unit. SI unit of energy is always joule only. But here usually when we are household application cases, that cases only we can say, okay, so there will use that watt hour. And this is also very small unit, you can see here. So this is a very small unit. Okay, so that is the reason. So when we are talking about the electrical energy, okay, in household, okay, there will use usually, so okay, kilowatt hour usually will use. Okay, so kilowatt hour commonly, this is commonly called as unit. So 1 kilowatt is a 1000 watt into 3, I mean 3600 second. So usually, so this is 3.6 into 10 to the power of 6 joules. Okay, so we'll see the problems based on this okay, electric power and electrical energy problems we'll see in next lecture. Okay, so from this we'll wind up the chapter. So thank you so much for watching this video, and please don't forget to subscribe and don't forget to like, don't forget to comment. Thank you so much. If you have any doubts, you can message in comment box, then surely I will give the reply. Thank you so much.